So for number 19, we have an ambitious and hungry group of Penn State graduate students that are synthesizing a new element called nitneon. They figure out the half-life, but then they go to get cookies. And so then they go to West Halls, get some cookies, and it takes them about an hour to do that. And they wonder how much nitneon will be left when they get back to lab. So I've organized some of the information from the problem here. We have the T1/2, and what we're trying to find is the ratio of what will be remaining after an hour to what we initially have. So we're trying to find NT over N0. And that time is 1 hour. And because it's just one element, this is a radioactive decay. And radioactivity always follows first order kinetics. So I wrote the equation here that's on the data sheet. This is the same as first order, it's just written a little differently for the nuclear stuff. And because it's first order, I wrote the first order half-life expression there too. And so there's two ways you can go about solving these, either using the negative KT part or the minus 0.693 T over T1/2 way. Both are fine, and I'll show you both here. Okay, so starting with way 1, we're going to use the natural log of NT over N0 being equal to negative KT. So, to solve this, we need to figure out what our K is, and that's going to be equal to the 0.693 divided by T1/2. So 0.693 divided by 1855 seconds. And our K comes out to be about 3.74 times 10 to the negative 4. And the unit on this, we're dividing by seconds, so it's going to be second inverse. Okay, so then we have an issue though, because we know that our time that it elapses is an hour, and we have our K in seconds. So we're going to need to get this 1 hour time into seconds. So we have 1 hour, and in an hour we have 60 minutes. And in 60 minutes we have, or in 1 minute we have 60 seconds. And so this 1 hour is equal to 3,600 seconds. And so that's the time we're going to want to use below. So we can set this up. So this is going to be equal to our K, negative K, times our time in seconds so that the units match. And so this natural log will be equal to negative 1.34. And so now to get rid of our natural log, we're going to use our exponential, and we'll have NT over N0 equal to e to the 1.34, negative 1.34, and that's going to end up being about 26%. I wonder if the cookies were worth losing 74% of their product. I don't know. Okay, and so that way's fine. We got to the 26% answer. But we can get there the same way, or to the same answer with the different strategy. So here for way 2, we're going to plug in, we'll have our natural log of nt over n naught, and it will be equal to negative 0.693 times that 3600 seconds divided by the half-life, which is 1855 seconds. And when you solve this, you'll again get the negative 1.34, and so you'll get nt over n naught still being equal to the exponential of negative 1.34, which is still 26%. So you can use either strategy. I just wanted to show that both are good, both are valid. The answer there is C. Okay, now we've traveled along, we've gone from Route 99 to Route 22, and we are at a different, some might say lesser, but different university called Pitt, and there they're synthesizing plutonium, a new element. And they synthesize the sample, and they get an activity of 160 disintegrations per second. 16 minutes later they measure it again, and they only see 10 disintegrations per second. They want to figure out what their half-life is. And so disintegrations per second is kind of a weird unit, but you can just think of it as being analogous to concentration. It gives you some sense of what the amount is. So we can use that like our N naught and our NT. And they want us to figure out what the half-life is. And the units on our answer choices are minutes. Okay, so we can keep that in mind when we're plugging things into this equation. And I'm just going to go straight to the ln of nt over n naught as being equal to the negative 0.693 t divided by t1/2 to solve for that. Okay. So plugging in here, I forgot to mark it, but our time is just going to be that 16 minutes. And we can leave it in minutes because our answer choices are in minutes. So we'll have the natural log of 10 disintegrations per second divided by our initial 160 disintegrations per second. Set that equal to negative 0.693 times our 16 minutes divided by t1/2. So this left side ends up being negative 2.77. And then with a little more algebra, we get that, that t1/2 is equal to just about 4 minutes. Making B the answer there. Here we're going to figure out the mass defect of a lithium-7 nucleus, and they tell us how much the atomic mass of one lithium-7 nucleus is. And we have a ton of sig figs, which will all be important, okay, so we're going to have to use all of the sig figs. So the mass defect is just some amount of mass that we think should be there if we just add up all the protons and neutrons, but that we don't see in the actual nucleus. And this is the mass that's converted to binding energy that holds the nucleus together. Okay, so I've written the symbol for lithium here, and we know that we have 3 protons because of the atomic number. And so that means we're going to have 4 neutrons, because the mass number is neutrons and protons. Okay, so we need to know how much a proton and a neutron weigh, and these numbers are on the data sheet. And so a proton weighs 1.007275 AMU, and a neutron weighs 1.00866649 AMU. So you don't have to memorize those are on the data sheet. Okay, so we're just going to say we have 3 protons and figure out how much the protons weigh, 4 neutrons, figure out how much those weigh, and add them together to see how much this nucleus should weigh. So we're going to have 3 protons, and we know in every 1 proton we're going to have 1.007275 AMU for a total of 3.0218295 AMU. We can do the same thing for the neutrons. So we have 4 neutrons, and each 1 neutron weighs that 1.00866649 AMU for a total of 4.0346596 AMU. So now we're just going to add those together to get what we expect the total mass to be. So the mass we get is 7.0564891 AMU. Okay, so that's our predicted mass for a lithium-7 nucleus. But I think if you look, you can see that these 2 masses aren't the same. And so we're just going to look for the difference between them. So we're going to have 7.0564891 minus 7.016003 for a mass defect of 0.0404861 AMU. Okay, and so we can see that luckily this matches D, so we don't have to worry about trying to convert into different units. Okay, so mass defect, all you gotta do is look at how many of each particle you have, how much each particle weighs, multiply it out, add them together, and then look at the difference. So for number 22, we have these spheres, and we're converting A to B, and they want us to figure out what the rate constant is for this reaction. So you can see that each of our time steps are 20 seconds, and I've gone ahead and counted how many of each type of sphere we have. So on the first one we have 12A with 0B, and then the second one we have 6A, 6B, and the third we have 3A, 9B. And so what I see happening here is that as we go from the first time to the second time, we've cut the amount of A that we have in half. So we've done one half-life. And the same goes for the next interval. We go from 6A and down to 3A, so we have another T1 half. So if we look here, the time interval is 20 seconds for that T1 half, and it's 20 seconds for this T1 half also, because we're going from 20 seconds to 40 seconds. And so when you have a constant T1 half like we do here, this is going to be first order. If the half-life had gone from like 20 seconds to 40 seconds, then we would know it's second order. And so we have our first order half-life expression. So T1 half is equal to 0.693 divided by K. And so we'll have 20 seconds is equal to 0.693 over K. And when we solve that, we get that K is equal to 0.0347-ish. This is going to be seconds inverse. And so that matches pretty closely to E. Hey guys, so I'm realizing I accidentally skipped number 18. I'm sorry about that, but I'm here doing it now. Sorry. Okay, and number 18, they're saying that we have a flask filled with some A, and with this reaction we know that 2A form 1B, and they want us to figure out how many moles of B are present at time point 40 seconds. Okay. And so what we know is that however many moles of A that have disappeared, we can relate that to the moles of B using the stoichiometry. So let's just figure out how many moles of A disappeared. So we started with 0.124 moles. We end with 0.054 moles. And so the difference here is going to be 0.07 moles of A that disappeared. And so this question is just simply asking how many moles of B will be there if this many moles of A disappear. So we can say the 0.07 moles of A that disappeared, and we know that we get 1 mole of B for every 2 moles of A as shown in the reaction above. And so to get moles of B, we just divide by 2, and we get 0.035 moles B. So this isn't even really a rate problem, it's more of just stoichiometry in the context of rates. Okay, so this is answer choice B, and you want to be careful that you have this equivalent set up the right way so that you don't accidentally get answer choice C. So always write out even the most simple calculations.